I welcome you to Smart Physics as we continue with our step-by-step walkthroughs. We are journeying through the Cambridge IGCSE Physics Component 41 of October-November 2025. In this video, I will zero in on question number 3, so let's quickly delve into it. Question number 3. Fig 3.1 shows a simplified diagram of a solar cell. Item A, describe the energy transfer in the solar cell. If you look at it carefully, you will see that the input is light. So light energy is the input and the output is electrical energy. Our output is electrical energy. Our output is electrical energy. Our output is electrical energy. Therefore, if we are to describe the energy transfer in the solar cell, we need to talk about the energy conversions in a description format, not stating. So we are going to have an ideal answer which says light energy from the sun is transferred into electrical energy in the solar cell. Part B of the same question suggests how black coating allows the solar cell to transfer more energy. Now, the interesting thing is you should know the properties of black color in terms of energy absorption and reflection. So black is a good absorber because it reflects less energy. So the ideal answer should be the black coating absorbs more light and reflects less. The black coat absorbs more light since it's less reflective when it comes to energy. So more light energy is available to be converted to electrical energy. With this, I will proceed to part C. Part C reads 0.72 kilowatts of light is incident on a solar cell in Fig 3.1. The cell has an efficiency of 75%. Item 1, calculate the output power of the cell. So I prefer selecting data, then we do the selection of the right equation. So what are we given? We are given input power 0.72 kilowatts and we're given the efficiency at 75%. I always prefer reducing my efficiency to decimal because it makes the equation easier to deal with. With this data, we can now record the equation for efficiency, which says efficiency is useful output power divided by input power. Our useful output power is the requirement of the question, hence we need to change the subject. Let's change the subject and make output power subject of formula. We will have output power is efficiency times input power. Once we reach this stage, the next thing is a quick substitution. 0.75, that's our efficiency, times 0.72, that's our input power, getting 0.54 kilowatts. Take note, the units are not given, so your answer is never complete without units. Number 2, I've presented my answer to a minimum of 2 significant figures. Avoid answers like 0.5. You round off to 1 significant figure. With this, the answer mark, you will lose it. Avoid 1 significant figure. All answers are supposed to be a minimum of 2 significant figures with an appropriate unit. Part 2 of C, state the meaning of the term kilowatt hour. Now, I want you to understand that kilowatt hour is energy. Kilowatt hour is energy. Remember, energy is equals to power times time. Now, kilowatt times hour will give us kilowatt hour. In other words, we have kilowatt, which is power, times time in hours, which is energy. So a kilowatt hour is a unit of energy. So what is a kilowatt hour? When a gadget of power rating 1 kilowatt runs for an hour, the energy consumed is a kilowatt hour. So the ideal answer for this particular question was A kilowatt hour is the amount of energy used or transferred when electrical power of 1 kilowatt is used for an hour. Right, with this we can quickly go to item number 3 of C. Item number 3 reads, energy is produced by each solar cell. So this is each solar cell. We need to underline this part because we use it. Each solar cell. Each solar cell. For an average of 6 hours per day. So each solar cell runs for an average of 6 hours per day. It doesn't run 24 hours, but 6 hours each day. A household uses approximately 7,400 kilowatts hour of electrical energy per year. So energy requirement per year is 7,400 kilowatts hour. Calculate the number of solar cells needed to produce energy for one household. Here we are given information about one solar cell, how much time it runs a day, and how much energy is required. So the first thing is we need to find energy produced by each cell per day. We go to energy produced by each cell per year. Then if we divide the energy requirement per year by the energy which is being produced per year, we find the cells required. So energy is power times time. For us to find energy in a day, we say power times time in a day. So each cell is rated 0.54 times 6 hours in a day, mounting up to 3.24 kilowatts hour per day. We take this to 365 days in a year. So we now have energy per year is 3.24 times 365, which is going to give us 1,182.6 kilowatt hour. This is energy per year. Now that we know the energy per year and the energy requirement per year, we can safely say number of cells is equal to energy required per year divided by the energy produced by each cell per year. Therefore, it requires 6.26 cells. It requires 6.26 cells to produce this energy in a year. But there is a very important aspect of the question said your answer must be as a whole number of solar cells. So should we pick 6 or 7? If we pick 6, they won't be producing 6.26. It will be less than 6.26. This fraction, where will it come from? This fraction, where will it come from? So we need to move to the next whole number, which is 7. 7 are the ones which can at least produce a minimum of this. So our final answer is supposed to be 7 cells. I hope you have been helped and you have enjoyed today's class as we continue our walkthroughs. See you in the next video when I'm dismantling question number 4.